Okay, so we are in principle recording right now. So welcome everybody to this TCS Plus talk. We're very happy to have Fotis Iliopoulos tell us today about stochastic local search and the Lovász Local Lemma. I'm not sure I'm pronouncing Lovász correctly. Fotis graduated recently from UC Berkeley, where he was supervised by Alistair Sinclair, and now is at Princeton University and the IIS at the Institute for Advanced Study for a postdoc. Fotis has done quite a lot of work on, well, things related to the LLL, but also and relatedly to finding and sampling solutions to CSPs and stochastic local search, and quite a few of those things he's going to tell us about today. Before starting, I'd like to give a shout out to the other organizers at TCS Plus. So that includes Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rosenstein, Oded Regev, Celil Schramm, Thomas Vidic, and Eric Weingarten. A little advertisement for the next talks. So the next 2 weeks, we're going to have Alex Wynn from NYU tell us about the low degree hardness of random optimization problems, and Susanna De Resende from KTH about lifting with simple gadgets and applications to circuit and proof complexity. So stay tuned for announcements. That's all for the prelude. So the floor is yours for this.
Thank you. And thank you for inviting me. So, so this is going to be a talk about constraint satisfaction problems, really, and how to solve them in certain cases. And instead of me giving you a formal definition for what a constraint satisfaction problem is, let me give you an example. So the example is the problem of Q-coloring graphs, where the input is a graph G and a set of Q colors. And the goal is to color the vertices of the graph so that no two adjacent vertices share the same color. And this is a constraint satisfaction problem in the sense that you can imagine a variable sitting on every vertex and a constraint sitting on every edge. And the constraint basically says, I want my variables, my endpoints to take different values. And we call the values colors. Of course, in general constraint satisfaction problems, each constraint could be associated with more than two variables. And in that sense, we have a hypergraph instead of a graph. And we don't just have coloring constraints. Each constraint could forbid pretty much an arbitrary set of assignments for its variables. As another example, in the problem of k satisfiability, the input is a set of n variables that are binary. They are taking values that are either true or false. And the constraints contain exactly k variables and forbid exactly one assignment. Okay, so for example, this is a three-stat constraint that forbids the assignment true, true, false. Now, constraint satisfaction problems have many applications in computer science and artificial intelligence, bioinformatics, etc. And of course, we would like to be able to solve them efficiently. But I think we all know that this is probably not an easy task because they are NP hard even to approximate. So a common direction people take is that they are trying to identify interesting families of instances of constraint satisfaction problems that are in fact tractable, yet interesting. So here are two examples. One example would be random instances. For example, what if we try to color a random graph? Okay, what can we say about that? Another example would be instances with specific deterministic instances that have specific structural properties. So for example, what if we try to color a triangle-free graph? Okay, and in this talk, actually, I'm going to talk about both of this type of examples and their relation. Okay. Now, towards that end, in this talk, we will mainly focus on and in our effort to find the tractability in instances of constraint satisfaction problems, we will focus on a class of algorithms which are called local search algorithms. And for this talk, a local search algorithm is defined as follows. So it's an algorithm that starts at an arbitrary configuration of the problem. So for example, in graph coloring, again, a configuration like this. And then while violated constraints exist, so these are violated constraints, then the algorithm will pick one, okay, say this one, and will take some action to fix it. Maybe in a simple scenario, maybe it changes values to its variables uniformly at random, okay, just as an effort to fix it. And the algorithm will keep doing that until hopefully it terminates and finds the satisfying assignment for the problem. Now, of course, this is far from a trivial a priori to understand whether this process will terminate, because each time you are making a step to fix one constraint, you could violate a new one or more than one other constraints, and this could keep going. And it's not clear, whether these processes are even useful, but they are. And in this talk, we will try to understand them at least from a certain point of view. Now, to that end, it turns out that this kind of processes have very deep connections to a very, very powerful tool from probabilistic combinatorics, which is called the Lovász Local Lemma, which at least when applied to constraint satisfaction problems, it says the following, okay? So imagine that you are given an instance of a constraint satisfaction problem and you want to prove that it is satisfiable, it has a solution. Then the local lemma says the following. So pick any probability distribution you want over the set of the configurations for each variables. So for example, in a simple case, you would pick a uniform distribution over the set of configurations for its variables. And now, with this distribution at hand, define one bad event for each constraint that basically says this constraint is violated if I draw a sample from my distribution. So this is one bad event for each constraint. And now the local lemma says that if each of these bad events is not very likely, so if the probability of violating a certain constraint when you draw a sample from the distribution you picked is at most p, say, and these bad events are mostly independent. So each bad event B is mutually independent of all, but at most delta other bad events. And P times delta is roughly speaking less than 1. Then with positive probability, if you draw a sample from this distribution you chose, then none of the bad events will occur. In particular, this means that every constraint will be satisfied. And in particular, this means that you have found the satisfying assignment. So the problem is satisfiable. Let me mention that while this is a tool that proves the existence of satisfying assignments, it's not a tool that can be used at least in its original form. It could not be used to efficiently find assignments, because the probability with which you land on satisfying assignments, even if all these conditions are true, is exponentially small in the number of bad events, in the number of constraints. Okay, so it would take a long time for you to see a satisfying assignment if you just performed naive sampling. Fortunately, 10 years ago, Moser and Tardos did this breakthrough work where they realized that a very simple local search algorithm, like the one I showed you earlier, can actually make constructive the local lemma in the most popular setting that it's applied, which is called the variable setting. Now, the variable setting is really when you have a constraint satisfaction problem and the distribution you are allowed to choose is allowed to be a distribution that basically picks independently a value for each variable. So in other words, you are allowed to use distributions that flip a coin for each of the variables independently. Okay, but this is still very powerful, and indeed it's the most popular form, the most popular setting in which the local lemma is used. And for this work, actually, Moser and Tardos very recently received the Gödel Prize. And rightfully so, because their work has inspired many other papers and many other directions. Here you see only a few of them, and the ones I am interested in and I have worked on. And I guess in this talk, the theme of this talk will be two things. So first of all, I will present a general framework for the analysis of this local search algorithms that is inspired by the local lemma. And second, I will show applications of these ideas to solving a class of instances that are called pseudo-random, a class of instances of constraint satisfaction problems that are called pseudo-random, and their connections to the so-called algorithmic layer. Okay, so let's start with the first part. Now, so this will be a framework for designing and analyzing local search algorithms like the one I showed you earlier. And it has two nice features. First of all, essentially all known LLL applications can be made constructive in this framework, even the ones beyond the variable setting. And two, actually, this setting provides tools and applications that actually go beyond the standard LLL. And roughly speaking, this talk is based on these three papers with collaborators, but mostly is based on a recent work with Dimitris Kleopoulos and Alistair Sinclair. Now, my goal will be to give you a flavor for what are the ingredients that one needs to, what are the quantities that one needs to control and take care of when trying to understand the behavior of a local search algorithm, at least in the eyes of this framework. And towards that end, instead of giving you the full generality, I will focus on a simple example and generalize from that. And the example is the application of the local lemma to the so-called to the k-sat problem, which is the following. So a straightforward application of the local lemma basically allows you to prove the following. So given a case in a formula such that every clause shares variables with fewer than 2 to the k over the other clauses, then it is guaranteed that this formula is satisfiable. And this is proved by applying the local lemma with a uniform distribution over the set of configurations of the variables of the formula, and noticing that the probability that a clause is violated under this distribution is 1 over 2 to the k. Okay, and also that clauses that do not share variables are independent in this distribution. Now, so this would be a sketch of the existential proof. If you want to find an algorithm that actually finds the solutions in this kind of instances, then you would employ this algorithm, which is essentially the Moser and Tardos algorithm. So what does this algorithm do? Well, it starts at an arbitrary assignment, sigma 1, and then while valued clauses exist, it picks one and it resamples its variables uniformly at random. So it flips a coin for each of the variables of the chosen formula. This is how it does the update. Okay. Now, the way the valued clause is chosen at each step can be arbitrary, really. But for the purposes of this talk, let me make things concrete and say that the algorithm will choose the lowest indexed valued clause. Okay, so this will make things a bit easier for the exposition. Good. So now that we know the algorithm, let's see how one would analyze it. Let's get a flavor. And the main technical insight of this work with Dimitris and Alistair was that all these LLL-inspired convergence arguments for local search algorithms can be viewed as a specific method for bounding the spectral radius of a matrix that is associated with the algorithm we're trying to analyze. Okay, so what do I mean by that? Well, let's see. So this algorithm I just described, this Moser and Tardos algorithm, is basically a Markov chain, right? So since it's a Markov chain, it has a transition matrix, which I have drawn here. Now, to explain what I've written here, let me introduce some notation. Omega will be basically the n-dimensional binary cube, where n is the number of variables of the formula, and omega star will be the float part of the state space, that is the set of violating assignments for the formula. Now, it could be that omega star and omega, it's the same thing. We don't know that, but let me use different notation for now. And with this notation, now the transition matrix of the chain looks as follows. So on the upper left side, you have this matrix A, this omega star by omega star matrix A that governs the transitions between the violating part of the state. So this matrix A tells you what is the probability to go from a state sigma to a state tau, as long as both sigma and tau are violating assignments. Now here B, which a priori could not exist, is the transition matrix that governs the transitions between the violating part of the space and the satisfying part of the space, if one exists. Here you have the identity because when you hit a solution, you stay there, and here you have 0 because once you've found the solution, you never go back to violating assignments. Good, so this is what the transition matrix looks like. And why is this helpful? Well, it's helpful because, I mean, a starting observation is that if you want to prove that the algorithm has not found a satisfying assignments in T steps, then you really need to look at the Tth power of matrix A. So here E of sigma 1 is the indicator vector for the initial state. And basically the fact that you have not found the satisfying assignment in T steps, it really means that all these transitions were governed by A. So it's like you're applying A T times, you know, on the original vector. Good. So why is this helpful? Well, because if you want to guarantee that no matter where you start from, then the algorithm will converge to a satisfying assignment. This is equivalent to say that the spectral radius of A, that is the magnitude of the eigenvalue with the largest magnitude, is strictly less than 1, or equivalently that the spectral radius of the Tth power of A goes to 0 as T grows, and therefore A to the T goes to 0 as T grows. And I mean, this is what we will be trying to establish. And to do that, it suffices basically to show that any operator norm of A to the T goes to 0 as T grows. And in particular, maybe after the change of basis, because change of basis with an invertible matrix retains the eigenvalues. And this is, in particular, in this case, we will use the one norm, and in the simple case of example, we will use no change of basis, although I will comment on the usefulness of a change of basis. Good. So now this is our new goal, show that the one norm of this matrix goes to 0. And the point is that all the local lemma inspired arguments out there, they establish this fact in 2 steps. So the first step is to consider a row decomposition of matrix A. In this example, the row decomposition would be as follows. So basically, for each clause Ci, you have a transition matrix Ai that governs the transitions of the algorithm when the algorithm tries to address clause Ci. That means that Ai of sigma tau will equal to A of sigma tau if Ci is the lowest indexed clause in sigma. So if it's the clause that the algorithm chose to fix in state sigma, and it will be 0 otherwise. In other words, AI keeps all the rows of the transition matrix that have to do with clause Ci, that is the states in which the algorithm would choose to address Ci. And therefore, it's not hard to see. I mean, by definition, A, it's basically the sum of these matrices. It's a row decomposition. Good. So this is the first step. And the second step is bounding the one norms of these matrices. This will have a combinatorial interpretation, and then using these bounds from the small matrices, from the sparse matrices to get a bound for the one norm of the A matrix. Okay. Now let me remind you at this point that the one norm of any matrix, it's basically the maximum column sum. And if you apply this this definition in the case example and the Moser and Tardos algorithm, you can see that the value you get is 1 over 2 to the k. I mean, this is a simple observation that I'm not going to establish now, because but I want you to notice that this is exactly the probability that a closed CI is violated if you were to pick a configuration uniform at random. So because each clause forbids one assignment for its variables, if you were to pick, a configuration for the variables of the formula uniform at random, you would get that the probability that the clause is violated is 1 over 2 to the k. And this is, by coincidence, this is not really by coincidence, but this is what you get here. And now what I want to explain is why you get that. Okay, so I want to give you a combinatorial interpretation of the one norm of these transition matrices. And at a high level, what the one norm does of these matrices, it measures, it's a measure of distance between two distributions. One distribution is the uniform probability distribution over the state space, over the configuration. The other one, which we call nu I, is a distribution that is induced by the actions of the algorithm. So, in particular, think of the following example, of the following experiment. Sorry. So, you pick a random assignment, a uniform random assignment for the variables of the formula, conditional on that constraint CI is violated. Okay, so basically, right, this is what I said. And then the algorithm takes a step on this sample to try to fix clause CI. And this induces the distribution nu I. In other words, distribution nu I is induced by the actions of the algorithm when you are addressing constraint CI in an average case environment, in a random state. Okay, so nu I, again, is the distribution induced by the actions of the algorithm when the algorithm tries to fix constraint CI, close CI, in a random state where CI is violated. So now you have nu I and the uniform probability distribution over omega, and I claim, and I'll show you in a minute, that the one norm is basically some notion of distance between these two distributions, and to get better results, you would like, ideally, you would like nu I to be equal to the uniform distributions. You would like these things to be close. But before formally explaining what's going on, let me tell you that there is nothing special about the uniform distribution. If you would like to perform an analysis of your algorithm with any other distribution, like in the local lemma, you can choose any distribution besides the uniform, then you would perform the same row decomposition, but now instead you would look at the one norms of matrices AI after you have performed a change of basis with a diagonal matrix that basically encodes the probability distribution that you chose. What do I mean by that? I mean that if mu is the probability distribution you chose, then matrix M will basically be a diagonal matrix whose sigma entry would be equal to the probability distribution, the probability mass mu of sigma that is assigned by your chosen probability distribution. And then again, this one norm would measure the distance between the probability distribution mu and the distribution induced by the actions of the algorithm when you try to address constraint CI in a random state where random now means random according to me. Okay.
Yeah. I have a question just to understand whether I like the intuition behind that. So basically, you want your algorithm to try to mimic as much as possible, like the distribution of actions of the algorithm to mimic as much as possible, like the distribution of with the dependencies in the LLL. Is that the interpretation? So that you add uniform in the case where there is actually no dependencies, and otherwise you try to see how well your algorithm aligns with that distribution mu.
So right, yeah. So it's basically what you said again. So you have a distribution in mind that is for the purposes of the analysis. It's the distribution you use to apply the local lemma. Let's say in the case of SAT is the uniform distribution over the configuration space. And now you want to see how well the algorithm mimics this distribution when it tries to fix a constraint. And I'm saying is that what matters is that the algorithm should I mean, the way things, sorry, the distribution mu I you care about is the distribution induced by the algorithm when it takes a conditional sample from the uniform distribution conditional on constraint CI being violated and addresses it at this point. Okay, so it's like, what is the average case performance of the algorithm? Okay, so I'm not sure.
Yes, thank you. Yeah. Thanks.
Yeah. Right, okay. One last time, and then I'll move on. Mu I is the distribution induced by the algorithm when you address a closed CI in a random state where CI is violated. And you want mu I to be the same as the uniform distribution, at least in the case of KSAT. Okay. Now, a bit more formally, and in an effort to try to formally explain what is this notion of distance between those two distributions, the one norm of the transition matrix mu inverse, where mu encodes, as we said, a probability distribution on its diagonal. After some manipulation, it turns out to be a product of two terms. The one term is the probability of the constraint being violated under distribution mu. So this is exactly what you have, the quantity you carry in the local lemma. What is the probability of your bad event? The other term has to do with this distance between the distribution mu I I've been trying to explain and your probability distribution of choice mu. And it's the Renyi divergence, basically, which is a fancy way to talk about the maximum point-wise ratio between distribution mu I and mu. Okay, so in an ideal scenario, like in the case of KSAT, where your algorithm really replicates and really mimics the distribution mu you chose, this second term will be one, and what you would be left with is the probability of the constraint being violated. Okay, so this is why we got 1/2 to the k in this example. Okay, and when mu I equals to mu, then we say that the algorithm is a sampling correct, and this is a notion introduced by Harvey and Forntrack in a very great paper they have. Cool. Now, okay, so to recap, we established that, at least in the case of KSAT, these swan norms have a combinatorial interpretation that allow us to argue that for each AI, the one norm of AI is 2 to the minus k. And now we want to see how to take these bounds and get a bound for the t power of a. And Here's very briefly the idea. So what you do is you write A as the sum of these matrices, and then you expand this sum. Okay, so you expand this sum to a sum of product of sequences. Okay, and what you do here basically is you only keep the sequences that survive. Okay, so you only keep the sequences that have a non-zero product. So I'm not doing anything fancy here. This is, trivial algebra, and exactly because you have this bound on the norms, what we're left with is you're trying to estimate what is the number of sequences of matrices that survive times 2 to the minus kt. Okay, and it turns out that again this product of matrices have a combinatorial interpretation. What is that? Basically, the product of matrix A1 times A2 times A3 and so on, basically it encodes what is the probability that the algorithm first addresses clause C1 and then addresses clause C2 and so on and so forth. And it turns out that the sparsity of the input, I'm not going to show this, but the sparsity of the input, the fact that each clause shares variables with a few other clauses, it allows you to map this set of surviving sequences to a set of forests that are delta forests and have T nodes and M roots, and then you can count them. While I'm not going to show you this counting argument because it's a bit technical, the key here the key idea here is that every time the algorithm tries to fix a clause, it can only introduce delta new other clauses. And this is because the algorithm, remember, only changes the variables of the clause, and each clause shares variables with at most delta other clauses. So the fact that when you are trying to fix a clause, you can violate at most delta others is kind of the key behind this counting argument. I'm not showing you now because you will not, it's well understood by now and it's a bit technical for this talk. And right, yeah, and this is where this comes from. So overall, if you have this bound of delta that we initially assumed, then indeed you see that, and combining these two facts, indeed you see that the spectral radius of A to the T goes to 0 as when T becomes roughly equal to the number of clauses. Okay. Now, what is important here is not so much to get the details of the proof as is to understand what are the kind of the qualities of the qualities that are good for an algorithm in the eyes of this analysis. And these are two things. One thing is that the actions of the algorithm should, in a certain sense, be compatible with the underlying probabilities space mu that you choose for your local lemma analysis. And this is reflected on bounds on the norms. And the second thing, which was reflected on this counting argument, was that every time you're trying to fix a constraint, you should have some sort of bound on how many other constraints you can violate. And this plays the role of dependencies in the existential form of the local lemma. If you want a more quantitative statement, here's a simple one. So imagine that you have a constraint satisfaction problem and then a local search algorithm that tries to fix it. And you choose an invertible matrix M, which encodes a probability distribution. Okay? Now, if for each constraint Ci, the one norm of this transition matrix AI is at most gamma, so this plays the role of probabilities in the existential version of the local lemma. And if whenever addressing a closed Ci, you will never violate any constraint outside a small set of cardinality at most delta. And this plays the role of dependencies in the existential form. And the gamma times delta is roughly less than 1, then you are guaranteed that your algorithm will terminate fast with high probability. Okay. This would be an algorithmic local lemma in this framework that applies not just to the Moser Tardos algorithm, but really any type of algorithm of this form. Let me mention that this is not the end of the story in at least 2 ways. So beyond an argument for fast convergence, one could ask more questions like this type of algorithms are they parallelizable? What is a bound on the number of solutions they can output? Can we solve max CSPs using these techniques? And all these questions have been studied, and at least in the eyes of this matrix framework, you can get a positive answer to all these questions as long as whenever Ci and Cj are constraints, Ci and Cj are independent in this LLL sense I explained, then you further have that their transition matrices commute. Okay, so this is a whole other argument that is not similar to what I just showed, but this is a nice feature of this perspective with matrices, that it boils down things to commutativity. And moreover, the second thing is that in fact you can go even beyond the LLL, okay, as follows. And this was actually the main result in this paper with Dimitris and Alistair. And the point is that the way you go beyond the LLL is that instead of considering decompositions where you have one transition matrix per constraint, now you have one transition matrix for each constraint and each set of constraints that it could possibly violate. So in particular, AI of S is a transition matrix that governs that consists of all the rows in which sigma, in which the algorithm chooses to fix clause Ci in sigma as before, but also in the process introduces the sets. I mean, it violates the sets of constraints in S. Okay, and norms of these more refined transition matrices have a similar interpretation as before, as a distance between two distributions. But now the difference is that you can be more refined in accounting for this distance because you have information, you have higher order information. Okay, so you have information about how a constraint I and the set of constraint S correlates with each other. And the main thing that this kind of theorem it's helpful with is that in fact it allows you to analyze a wider class of algorithms that not only can resample when they are trying to fix a constraint, but if they don't like the outcome of what they see, they can backtrack. Okay, and in the rest of the talk, actually, I'm going to talk about applications of this type of theorem, which I think it's more interesting than trying to talk abstractly about what it is. Okay, and right, so here's the second part of the talk, which is applications of the first part to a class of constraint satisfaction problems that we call pseudo-random, and their connections to the so-called algorithmic barrier. Right, so again, instead of talking generally, let me talk about graph coloring. In particular here, I'm interested in the problem of Q-coloring a random regular graph, okay, for simplicity. We'll see how these things generalize later. Now, what is a random regular graph? So we consider the model, basically the distribution over the family of delta regular graphs with n vertices. So we pick such a graph at random, and we want to see how it behaves with respect to the coloring problem. And this is, as you can imagine, this is a very well-known and very well-studied problem. And it turns out that there is a phase transition in the sense that the model passes from being with high probability too colorable to being with high probability not too colorable at roughly 1/2 delta over log delta. In other words, the chromatic number of delta regular graphs is asymptotically at least 1/2 delta over log delta. Okay. Now, let me stress that this is about the existence of solutions, and it's not about finding solutions. If you want to talk about algorithms about efficiently finding solutions, then there is another bizarre phenomenon that takes place, which is the following. So it turns out that the algorithms we know seem to stop working at roughly double the number of colors. That is, the best algorithms we have need at least delta over log delta colors to be able to efficiently color a random delta regular graph. Okay, that means that there exists a regime here with the question marks where we know that solutions exist with high probability, but no algorithm that we know of can find one. And this is a kind of strange and bizarre phenomenon that has been studied, and it turns out that it's not a coincidence in the following sense. We do not know if there is a hardness a computational hardness phase transition there in terms of how a theoretical computer scientist would define it. So no, we don't know any NP hardness there or anything like that. What we do know is that at this point there, where our algorithms seem to stop working, there is a phase transition in the geometry of the solution space of the problem. Okay, what do I mean by that? Here on the right, what I have drawn is a large gray ball. Now I want you to imagine that each point of this gray ball is basically a Q coloring of a proper Q coloring that is a solution of the graph. And the reason I have drawn this as a ball is that the solution space is very well connected in the sense that you can jump from one solution to another by changing, let's say, the color of one vertex. Okay, and with this operation, you can basically navigate the whole solution space. So this is what happens when in the regime where our algorithms work. Now, in the regime that our algorithms do not work, here's what happens. So exactly at this point, this huge ball shatters into a number of smaller balls or clusters that while they are well connected on the inside, they are well separated in the sense that if you want to go from one cluster to another, then you need to go through configurations of the state space that violate many constraints, so a linear number of constraints. And this seems, and sometimes probably this seems that it makes it hard for our local search algorithms to find solutions. And since local search it's the best thing we have for CSPs and at least random CSPs, then we are stuck here. Let me tell you that this phenomenon, it's not just for Q coloring random graphs. It's for Q color. Sorry, it's not just for Q coloring regular random graphs. It also appears when you're trying to color, irregular random graphs, and it also appears you have a similar picture in other constraint satisfaction problems like KSAT, hypergraph coloring, hypergraph to coloring, max KSAT, in the sense that there always exists a satisfiability threshold, a threshold on the density at which the problem is solvable, but our algorithms seem to stop working at much lower densities. Okay, and so you have this algorithmic barrier, and you have this picture where the solution space changes from being well connected to shattered. Now, let me also point out that this phenomenon was first predicted non-rigorously by statistical physicists, But in many cases, it has been proven recently, the recent years, the last decade, via a large line of work by mainly TCS people. And now, why am I telling you all this? Okay, so this is the question I care about. So the question I care about it is, can algorithmic success up to the algorithmic barrier for each CSP be ascribed to a simple deterministic structural property of the input? That is, why do our algorithms work? Do they need the full randomness of the input? Or is there a simple property that any instance that has this property, it's tractable, and it happens that all random instances do have this property up to the algorithmic barrier. So this is the question I care about, and I think you will understand it even better if I show you the answer, at least in the regular graphs model. So in this model, it turns out that local sparsity is all that matters. So let me explain what I mean by that. So a recent result of Molloy says that triangle-free graphs of maximum degree delta can be efficiently colored via a local search algorithm that can be analyzed with the tools I was showing you in the first part of the lecture, and requires delta over log delta colors. Now, let me remind you that this is exactly the point where this algorithmic barrier phase transition starts at delta over log delta, which is twice the number of the chromatic number. And this is nice because this result really applies to random graphs as well, because random regular graphs are essentially high girth graphs. So basically, for any constant k, you expect that you will have only a constant number of cycles of length greater than k, and so you can easily form a high girth graph of any constant girth by removing a relatively small number of edges. And furthermore, these edges will form a matching, so this would not really affect the chromatic number. So you can really use this algorithm of Molloy to color random regular graphs up to the algorithmic barrier. But the nice thing about it is that Molloy's result matches the algorithmic barrier while applying to every triangle-free graph. Okay, while previous type of analysis uses for random graphs uses many more properties of the random model. And in that sense, triangle freeness is a sufficient pseudo-random property for coloring. So it's all you need to match the algorithmic barrier, which in my opinion, since it's so local, it's quite bizarre and very cool. And in fact, we know we can improve this result of Molloy. So in this paper with Dimitris and Alistair, we showed that even a random graphs with a linear random with a linear number of triangles are still pseudo-random as long as each vertex is contained in a few triangles. Okay, so as long as the graph is locally sparse. And even more so, in a couple of months ago, Davis and al. Showed that there is nothing special about 3 cycles. There's nothing special about triangles. Any graph in which each vertex is contained in at most roughly delta to the epsilon k cycles for any fixed k are still pseudo-random and have this nice property with respect to graph coloring. Okay, and by the way, all these results are proved by applying a sophisticated local search algorithms that are analyzed via this new algorithmic tool that I was talking about earlier. Cool. Now, let me at least give you some intuition for what kind of thing this Molloy's algorithm, at least, and our algorithm and Davis and et al. Algorithm uses when they are trying to to construct an algorithm for coloring. Okay, so I'm just going to give you the intuition for triangle-free graphs because I think it's kind of interesting actually. So the intuition is as follows. So fix a vertex v of your graph your triangle-free graph, okay? So it looks like this. It has delta neighbors, and there is no edge, in the neighborhood because the graph is triangle-free, right? And what you are trying to exploit here is that exactly because the graph is triangle-free, colors can be repeated in the neighborhood, okay? So you do not really need delta colors to color all the neighbors. You actually might need fewer colors because colors can be repeated. In fact, here's an interesting phenomenon. Say that a color is available for V in a case where you have assigned the colors to its neighbors. If assigning the color to V does not create any monochromatic edge. So for example, here, purple would be an available color for V because purple does not appear in the neighborhoods of V, okay? Now here's a cool phenomenon, okay? If you fix a vertex and you color its neighborhood at random with two colors, then there is kind of a local phase transition that takes place. So if you use let's say 1 plus epsilon delta over log delta colors, then you expect that with high probability, you will have a reasonable amount of available colors for V. So you can locally complete the coloring, okay? So you will have at least delta to the epsilon available colors. Now, if you use just 1 minus epsilon delta over log delta, somewhat fewer colors, then with high probability, this leaves no available color for V. And this is, by the way, all these are simple coupon collector arguments. Okay. And so and remember that delta over log delta is exactly the point where this algorithmic barrier phenomenon starts. Okay, so we see here that this kind of, if you want, local phase transition on the number of available colors for V in a random coloring of its neighborhood kind of predicts, in a sense, where the phase transition for the whole problem will take place, okay? And this is what the algorithms that use 1 plus epsilon delta over log delta, for example, Molloy's algorithm, is trying to do. I mean, it's trying to exploit, in the sense that it tries to move in a way so that at every point of the execution, vertex V thinks that its neighborhood, it's colored randomly. So while this might not be the case, I mean, in a strict sense, at least in a pseudo-random sense, this is the case, and this means that at any point, the vertex V has enough colors to color itself if needed, and so the way you impose this pseudo-random property that every vertex should feel like that its neighborhood, it's colored randomly, at least when it comes to the number of available colors it has. It's really simple. It's you add the constraint that's saying that says, I want not just proper coloring. I want every vertex to feel like it has many available colors, and you are also pursuing this type of constraints first, okay? And then you are trying actually to pursue proper coloring constraints. Right, so we're reaching the end of my talk, and here are a couple of questions. What about sparse random graphs that are not regular? So what about sparse random graphs that have average degree delta? Now, it turns out that this is somewhat technical, but it's not too hard, because they can also be treated essentially as high girth graphs of maximum degree delta. So the previous results still apply. So in that sense, in the general coloring problem of coloring sparse random graphs, again, local sparsity is the pseudo-random property that explains the tractability all the way to the algorithmic barrier. So the real question is, what about other KCSPs? Okay, what about cases, for example? And the answer here is kind of, I mean, there is strong evidence that suggests that local sparsity is again all you need. That basically, if, for example, the underlying hypergraph of your K-set formula has large girth, then this is all you need. And this is true for every KCSP of interest, really. But this is left to be proven because dealing with constraints of largearity is actually quite technically demanding. Nevertheless, in this recent paper I'm mentioning here is I made some progress when it comes to coloring K-uniform hypergraphs. Okay, so it's a first step in trying to deal with constraints of largearity, but but the belief is that for every CSP, local sparsity is really all that matters. Cool. Okay, so to recap in this talk, if there is anything if there are two things to keep in mind after this talk, are the following. So LLL-inspired local search algorithms can be analyzed by studying norms of appropriate transition matrices. And local sparsity is probably the pseudo-random property behind the selectability of random KCSPs up to algorithmic barrier. And this is certainly the case for graph coloring. Okay, thank you. Let me know if you have any questions.
Thanks for the talk. Is there any question from the audience? If so, you can type it in the chat or you can raise your hand.
I see one.
Oh. I think, where is it? Where is it? Okay, I'm just gonna see if I can ask people to unmute. So if you have a question, feel free to ask it right now.
No, I think.
Okay, thanks. Yeah, thanks. I couldn't. Nice talk. I just had if you just go back 2 slides, I just had a quick question on the last bullet there. Just I was just wondering. So is that? Do you mean that is this just a thought experiment that where you're coloring the neighbors of V IID with random colors, or your uniform IID colors, or is this for a random coloring, a uniform random coloring of the whole graph?
No, it's IID.
Okay, so it's just a thought experiment with
it's thought experiment, yeah.
Yeah, okay, thanks.
Yeah.
Thanks again. So unless there's another question, I'm gonna take us offline, and then like if you have questions you want to ask off the record, you can all go. Before we go, again, just an announcement. So the next 2 weeks at TCS Plus, we will have Alex Wen from NYU talking about low degree hardness of random optimization problems, and then Susana de Rosende from KTH about lifting with simple gadgets and applications to circuit and proof complexity. So stay tuned for the announcements. Thank you. And thanks to Fotis.